Once again, welcome you all in this session of internal combustion engine fuel and lubrication. In last lecture, we have discussed about the basic introduction of internal combustion engine and nomenclature of internal combustion engine, and we have also discussed some thermodynamic terms related to internal combustion engine like compression ratio, clearance ratio, and in this lecture we will continue about the introduction of about the working of Otto, diesel and dual cycle. So starting with the working of Otto cycle, Otto cycle it is also known as constant volume cycle, because in case of Otto cycle, heat addition takes place at constant volume. So if we make the PV and TF diagram for Otto cycle, so you can see from here PV diagram, pressure volume diagram for Otto cycle. First we will make isentropic compression process, and during this process the mixture of air and fuel compress isentropically inside the cylinder piston arrangement, and due to compression the volume decreases and pressure increases. So 1 to 2 is isentropic compression process, isentropic compression. And when piston will reach at top dead center, then at that time with the help of a spark plug, sparking is initiated at when piston reaches at the top dead center. Then at that time combustion of fuel and air will start, and due to the combustion of fuel and air, pressure inside the combustion chamber increases very rapidly and reaches a maximum pressure, that is 3. And process 2 to 3 is known as constant volume heat addition process. And due to this maximum pressure, piston will move from top dead center to bottom dead center isentropically, and process 3 to 4 is known as isentropic expansion process, and process 4 to 1 is known as constant volume heat reaction process, constant volume heat reaction process. At this point 4, exhaust valve is open, and due to pressure difference, exhaust gases from the engine will automatically go out to the atmosphere, because inside the combustion chamber the pressure of the exhaust gases is 3 to 4 times more than the pressure of atmospheric pressure. So due to this pressure difference, exhaust gases will move out from the engine to the engine cylinder to the atmosphere. So this is the PV diagram, pressure volume diagram for Otto cycle. Similarly, temperature entropy diagram in case of Otto cycle is, as we know that process 1 to 2 is isentropic compression process. So on the TF diagram, process 1 to 2 is isentropic compression process, and 2 to 3 is constant volume heat addition process. And we know that in case of TF diagram, this is the constant volume process. In case of TF diagram, this is the constant volume process, constant volume heat reaction. And 3 to 4 is the isentropic expansion process, and during this expansion temperature decreases. 3 to 4 isentropic expansion process, and process 4 to 1 is constant volume heat reaction process. So this is the PV and TF diagram for Otto cycle. Now we have to calculate the efficiency in case of the Otto cycle, and we know that efficiency in case of the Otto cycle is equal to work done upon heat addition, and we also know that work done is equal to heat addition minus heat rejection upon heat addition. It will be equal to 1 minus heat rejection upon heat addition, 1 minus heat rejection upon heat addition. So for the calculation of the thermal efficiency of Otto cycle, our target is to calculate heat addition and heat rejection in case of the Otto cycle. So if we look on the PV and TF diagram for the process 1 to 2, process 1 to 2 is isentropic compression process, and volume at 1 is the volume of gases before compression, and volume at 2 is the volume of gases after compression. And we also know that from the last class, compression ratio small r is defined as volume before compression to the volume after compression. So R is equal to V1 by V2 is known as compression ratio. And similarly, expansion ratio, we know that the process 3 to 4 is the isentropic expansion process. So the ratio of volume during the expansion process V4 by V3 is known as expansion ratio, And from the PV diagram, V4 is equal to V1, and V3 is equal to V2. And we already know that V1 by V2 is the compression ratio. So V4 by V3, that is the expansion ratio, is equal to compression ratio. So we can say that in case of the Otto cycle, compression and expansion ratios are same. So you can see from here, compression ratio is V1 by V2 and the expansion ratio is V4 by V3, that is also equal to V1 by V2. V3 is equal to V2 and V4 is equal to V1. So expansion ratio is equal to compression ratio is equal to small r in case of the Otto cycle. And we know that efficiency is equal to work done upon heat addition minus heat rejection upon heat addition is equal to 1 minus HR upon HA. So if we put the value of HR and HA, we will find out the value of thermal efficiency in case of the Otto cycle. So 1 minus from the TF diagram, we can calculate that we know that process 2 to 3 is the constant volume heat, it is heat addition process, constant volume heat addition process, and process 4 to 1 is the constant volume heat rejection process. So the value of HR, the value of heat rejection from the TF diagram, it will be equal to MCV T4 minus T1, So HR is equal to MCV T4 minus T1, MCV heat rejection process 4 to 1, MCV T4 minus T1, and heat addition from the TF diagram, process 2 to 3 is the heat addition process, and it will be equal to MCV T3 minus T2. So MCV will cancel out. So it will be equal to 1 minus T4 minus T1 upon T3 minus T2. That is the thermal efficiency of Otto cycle in the temperature format. But generally we have to convert thermal efficiency into the compression ratio format. So from the process 1 to 2, process 1 to 2 is isentropic compression process. So T1 by T2 will be equal to V2 by V1. So you can see from here, T1 by T2 is equal to V2 by V1 to the power gamma minus 1. If we look in the process 1 to 2, that is isentropic compression process. So T1 by T2 will be equal to V2 by V1 to the power gamma minus 1. And we know that V1 by V2 is equal to compression ratio R. So V2 by V1 will be equal to 1 by R. So T1 by T2 will be equal to 1 by R to the power gamma minus 1. And in the process, similarly in the process, isentropic process 3 to 4, T4 by T3 will be equal to V3 by V4 to the power gamma minus 1. And we know that V3 is equal to V2 and V4 is equal to V1. And we also know that V1 by V2 is the compression ratio. So V2 by V1 will be the 1 upon compression ratio. So it will be equal to 1 by R to the power gamma minus 1. So from here you can see that T1 by T2 is equal to 1 by R to the power gamma minus 1, and similarly T4 by T3 is also equal to 1 by R to the power gamma minus 1. So we can say that T1 by T2 is equal to T4 by T3, or T4 by T3 is equal to T1 by T2. So T4 by T3 is equal to T1 by T2, and similarly from the common mathematics we also know that T4 minus T1 upon T3 minus T1 is equal to T4 by T3 or T1 by T2. And we know that T4 by T3 or T1 by T2 from here is equal to 1 by r to the power gamma minus 1. So from here we can find out T4 minus T1 upon T3 minus T3 minus T2 is equal to 1 by r to the power gamma minus 1. And this expression is equal to 1 by r to the power gamma minus 1. So the thermal efficiency of Otto cycle will be equal to 1 minus 1 by r to the power gamma minus 1. So this is the expression of the thermal efficiency of Otto cycle in term of the compression ratio small r. In term of the compression ratio small r. So next is working of diesel cycle. It is also known as constant pressure cycle, because in case of the diesel cycle, heat addition takes place at constant pressure. So it is also known as constant pressure cycle. So PV diagram in case of the diesel cycle is process 1 to 2 is reversal adiabatic or isentropic compression. Process 2 to 3 is constant pressure heat addition process. And process 3 to 4 is isentropic expansion process. And process 4 to 1 is constant volume heat rejection process. 1 to 2 is isentropic compression. 2 to 3 is constant pressure heat addition. 3 to 4 is isentropic expansion process. And similarly we make the TF diagram for diesel cycle. So TF diagram for diesel cycle is process 1 to 2 is isentropic compression process. So isentropic compression, vertical line, it will be vertical line 1 to 2, and during compression temperature will increase, so the direction of the arrow will be upward. So process 1 to 2 is isentropic compression process. Process 2 to 3 is constant pressure heat addition process. So the constant pressure line on the TF diagram is like this: constant pressure heat addition process. And process 3 to 4 is isentropic expansion process, and due to expansion temperature decreases. And process 4 to 1 is constant volume heat rejection process. So this is the PV and TF diagram of the diesel cycle. Similarly, we have to calculate the thermal efficiency of the diesel cycle, and we know that the thermal efficiency of the diesel cycle is equal to work done upon heat addition. This suffix P represent here heat addition takes place at constant pressure. So the thermal efficiency of diesel cycle is equal to work done upon heat addition, and we also know that work done is equal to heat addition minus heat rejection. So it will be equal to heat addition minus heat rejection upon heat addition, or 1 minus heat rejection upon heat addition. So our focus is to calculate heat addition and heat rejection in case of the diesel cycle. So from the TF diagram, heat rejection is equal to M CV T4 minus T1, and heat addition is equal to M CP T3 minus T2. If we put the value of heat rejection and heat addition in this expression, it will be equal to 1 minus mCV T4 minus T1 minus T1 T4 minus T1 upon MCP T3 minus T2, MCP T3 minus T2. So mass will cancel out from numerator and denominator, and we know that Cp by Cv is equal to gamma. So efficiency in case of the expression of efficiency in case of the diesel cycle will equal to 1 minus T4 minus T1 upon gamma times T3 minus T2 upon gamma times T3 minus T2. So this is the thermal efficiency of the diesel cycle in terms of the temperature. So generally we have to convert this temperature this temperature format in the compression ratio and cutoff ratio. So new term from this in this diesel cycle is come into the picture, that is the cutoff ratio. So cutoff ratio is the 0.3 is known as cutoff point, because in case of diesel cycle fuel supply cut at 0.3 and start at 0.2. So the ratio of volume V3, so the volume ratio V3 by V2 is known as cutoff point, and it is represented by term rho, which is known as cutoff ratio. So our focus is to calculate thermal efficiency of diesel cycle in terms of compression ratio R and cutoff ratio rho. So for that we will convert temperature T2 in compression ratio and cutoff ratio, T3 in compression ratio and cutoff ratio, T4 in compression ratio and cutoff ratio. So we have to convert. So from the process 1 to 2, T2 by T1 is equal to V1 by V2 to the power gamma minus 1. So from here we know that V1 by V2 is equal to R to the power gamma minus 1. So from here T2 will be equal to T1 R to the power gamma minus 1, So here T2 is converted in terms of compression ratio and T1. Similarly, process 2 to 3, that is constant pressure process. So in process 2 to 3, T3 by T2 is equal to V3 by V2, and we know that V3 by V2 is cutoff ratio rho is equal to rho. So from here T3 will be equal to T2 times rho, and we also know that T2 is equal to T1 R to the power gamma minus 1. So if we put the value of T2, T1 R to the power gamma minus 1 times rho. So T3 is also converted into in term of compression ratio R, cutoff ratio rho, and temperature T1. And in process 3 to 4, process 3 to 4, that is isentropic compression process, T4 by T3 is equal to V3 by V4 to the power gamma minus 1. And we know that from here we know that V3 by V4 is equal to V3 by V4. You can see from here PV diagram, V4 is equal to V1 because process 4 to 1 is constant volume process. So V3 by V4 will be equal to V3 by V1 because V4 is equal to V1. So V3 by V4 is equal to V3 by V1, or we can also write here V3 by V2 into V2 by V1. And we know that we know that V3 by V2 is cutoff ratio, V3 by V2 is cutoff ratio, and V1 by V2 is compression ratio. So here V3 by V2 is equal to cutoff ratio rho, and V1 by V2 is the compression ratio. So V2 by V1 will be the 1 by R, 1 by compression ratio. So the value of V3 by V4 is equal to rho by R, cutoff ratio by expansion ratio. So it will be equal to rho by R to the power gamma minus 1. Gamma minus 1. So from here, T4 will be equal to T3 times rho to the power gamma minus 1 upon R to the power gamma minus 1. And we have already calculated T3 is equal to T1 compression ratio to the power gamma minus 1 into rho. If we put the value of T3 in this expression, T1 R to the power gamma minus 1 into rho, and already we have rho to the power gamma minus 1 upon R to the power gamma minus 1. So R to the power gamma minus 1 will cancel out, and T4 will be equal to T1 rho to the power gamma. T1 rho to the power gamma. So we have calculated T2 in term of T1 R to the power gamma minus 1, T3 in term of temperature, compression ratio and cutoff ratio, and T4 in term of T1 and cutoff ratio. If we put the value of T2, T3 and T4 in this expression, in this expression of thermal efficiency of the diesel cycle, so we will find out neta P is equal to 1 minus T4 minus T1 upon gamma times T3 minus T2. If we put the value of T4, T3 and T2 in the above expression, so it will be equal to 1 minus the value of T4 is T1 rho to the power gamma minus T1 upon the value of T3 is T1 R to the power gamma minus 1 rho, T1 R to the power gamma minus 1 times rho minus T2 is equal to T1 R to the power gamma minus 1. T1 R to the power gamma minus 1. So from here T1 will be cancelled out from the numerator and denominator. So neta P will be equal to 1 minus rho to the power gamma minus 1 upon gamma times R will be also common from this bracket. So gamma times R to the power gamma minus 1 rho minus 1. So this is the expression of the thermal efficiency of diesel cycle in term of compression ratio R and cutoff ratio rho. And we have already calculated thermal efficiency of Otto cycle is equal to 1 minus 1 by R to the power gamma minus 1, and thermal efficiency of diesel cycle is equal to, we can remember this expression by this method, 1 minus 1 by R to the power gamma minus 1. This is the thermal efficiency of Otto cycle into rho minus 1 upon rho minus 1 to the power gamma, and we have to multiply gamma in this denominator. So by this method we can remember the thermal efficiency of the diesel cycle. So this is all about the thermal efficiency of Otto and diesel cycle. So next topic is the dual combustion cycle or semi diesel cycle. Dual combustion cycle or semi diesel cycle. In case of dual combustion cycle, as its name suggests, it is having the properties of both Otto cycle and diesel cycle. So that's why it is known as dual combustion cycle. And we know that in case of the Otto cycle, heat addition takes place at constant volume, and in case of the diesel cycle, heat addition takes place at constant pressure. So as its name suggests, dual cycle. So in this case, in this cycle, heat addition takes place at constant volume and at constant pressure. So process 1 to 2, process 1 to 2, process 1 to 2 is isentropic compression process. Process 2 to 2 dash, process 2 to 2 dash is constant volume heat addition, and process 2 dash to 3, process 2 dash to 3 is constant pressure heat addition, and process 3 to 4, process 3 to 4, process 3 to 4 is isentropic expansion process, and process 4 to 1, process 4 to 1 is constant volume, process 4 to 1 is constant volume heat rejection process. So in this cycle, in the PV diagram, heat addition takes place at constant volume and at constant pressure. So that's why it is known as dual cycle, because it is having the properties like Otto and diesel both. So that's why it is known as dual cycle, dual combustion cycle. It is also known as semi-diesel cycle because the fuel is used as a diesel in case of the dual cycle. So that's why it is known as semi-diesel cycle. So TF diagram, temperature entropy diagram for the dual cycle is process 1 to 2, process 1 to 2 is isentropic, process 1 to 2 is isentropic compression process. Process 2 to 2 dash, process 2 to 2 dash is constant volume heat addition process. Process 2 dash to 3 is constant pressure heat addition process, and process 3 to 4 is isentropic expansion process, and process 4 to 1, process 4 to 1 is constant volume heat rejection process. So this is the PV and TF diagram in case of the dual cycle. So our target is to calculate the thermal efficiency of the dual cycle, and we know that thermal efficiency is equal to work done upon heat addition, and work done is equal to heat addition minus heat rejection upon heat addition. So it will be equal to 1 minus heat rejection upon heat addition. So our target is to calculate heat rejection and heat addition in case of the dual cycle. But before that, we know that V1 by V2 is the compression ratio small r is equal to V1 by V2, and process 2 to 2 dash, the ratio of pressure P2 dash, the ratio of pressure P2 dash upon P2 is known as explosion ratio. New term come in case of the dual cycle is the explosion ratio. It is the ratio of pressure P2 dash upon P2. Generally, explosion ratio is represented by the term alpha, and we already know that from the diesel cycle, V3 by V2 or V2 dash, V3 by V2 dash or V3 by V2, because V2 is equal to V2 dash is equal to cutoff ratio rho, and expansion ratio V4 by V3 is equal to V1 by V3, because from the PV diagram V4 is equal to V1. So, V1 by V3, and we can also write it as V1 by V2 into V2 by V3, and we know that V1 by V2 is equal to compression ratio, and V3 by V2 dash or V3 by V2 is equal to cutoff ratio. So, V2 by V3 will be 1 upon cutoff ratio. So, this ratio, so this term will be equal to R by rho. Expansion ratio V4 by V3 is equal to R by rho. So, our aim is to calculate the thermal efficiency in case of the dual cycle, that is equal to 1 minus heat rejection upon heat addition. So, focus is to calculate heat rejection and heat addition. So, from here you can see that heat rejection is equal to mCV T4 minus T1, and heat addition at constant volume is equal to mCV T2 dash minus T2, and heat addition at constant pressure is equal to mCP T3 minus T2 dash. So, if we put the values of heat addition and heat rejection, so the thermal efficiency in case of the dual cycle will be equal to 1 minus HR upon HA, and we have already calculated HR mCV T4 minus T1 upon mCP heat addition process 222 dash is constant volume heat addition process. So, constant volume heat addition process. So, it will be heat addition will equal to mCV T2 dash minus T2, and process 2 dash to 3 is constant pressure heat addition process. So, heat addition will equal to mCP T3 minus T2 dash. So, mass from the numerator and denominator will cancel out, and Cv also it will be cancel out, and it will equal to gamma. So, if we put the values of T4, T2 dash, T2, T3 and T2 dash in this expression in the format of R compression ratio, rho cutoff ratio and alpha explosion ratio. So, the thermal efficiency of the dual cycle will be converted in term of R compression ratio, cutoff ratio, rho and explosion ratio alpha. So, our target is to calculate T2, T2 dash, T3 and T4 in terms of R, rho, alpha. So, from the process 1 to 2, that is isentropic compression process, T2 by T1 is equal to V1 by V2 to the power gamma minus 1, and V1 by V2 is compression ratio R to the power gamma minus 1. So, from here T2 will be equal to T1 R to the power gamma minus 1. So, we have calculated T2 in terms of the compression ratio. Similarly, in the process 2 to 2 dash, that is constant volume heat addition process, 2 to 2 dash constant volume process. So, P2 dash by P2 will be equal to T2 dash by T2. So, from here T2 dash will be equal to T2 times alpha explosion ratio, because we have already discussed the ratio of pressure in the process 2 to 2 dash is known as the explosion ratio alpha. So, P2 dash by P2 is equal to alpha, T2 alpha, and we have calculated here T2 in term of the T1 and compression ratio. So, T2 will be equal to T1 R to the power gamma minus 1 into alpha, T1 R to the power gamma minus 1 into alpha. So, T2 dash is also converted in term of the compression ratio and explosion ratio. So, if we move to the process 2 dash to 3, that is constant pressure process. So, in constant pressure process T3 by T2 dash will be equal to V3 by V2 dash or V3 by V2, because process 222 dash is the constant volume process. So, V2 dash will be equal to V2, and V3 by V2, you can see from here, V3 by V2 dash or V3 by V2 is equal to the cutoff ratio rho. So, T3 by T2 dash will be equal to the cutoff ratio rho, and from here T3 will be equal to T2 dash times rho, and we have already calculated the value of T2 dash is equal to T1 r to the power gamma minus 1 into alpha. So, if we put directly the value of T2 dash, so T3 will be equal to T1 r to the power gamma minus 1 into alpha into rho. So, the value of T3 is also converted in the format of R, alpha, rho and T1. So, the next process is the process 3 to 4, that is isentropic expansion process, and in that process T4 by T3 is equal to V3 to the power V3 by V4 to the power gamma minus 1, and we have calculated here expansion ratio V4 by V3 is equal to R by rho. So, V3 by V4 will be equal to rho by R. So, the value of V3 by V4 is equal to rho by R to the power gamma minus 1. So, from here T4 will be equal to T3 times rho to the power gamma minus 1 upon R to the power gamma minus 1. And we have calculated the value of T3 is equal to T1 r to the power gamma minus 1 alpha rho. So, T1 r to the power gamma minus 1 alpha rho into rho to the power gamma minus 1 upon r to the power gamma minus 1. So, r to the power gamma minus 1 gamma will cancel out. So, from here T4 will be equal to T1 alpha rho to the power gamma. So, all the temperature is converted in the format of T1 alpha r rho. So, from here you can see from here, if we put the values of T4 in this expression, T4, T2 dash, T2, T3 and T2 dash. So, the thermal efficiency of dual cycle will come in the format of R, alpha and rho. So, the thermal efficiency of dual cycle is equal to 1 minus T4 minus T1 upon T2 dash minus T2 plus T2 dash minus T2 plus gamma times T3 minus T2 dash, gamma times T3 minus T2 dash. Okay. So, we will put the values of T4, T3, T2 dash and T2. So, if we put the values of T4, so the value of T4 is T1 alpha rho to the power gamma, T1 alpha rho to the power gamma, and T2 is equal to T1 r to the power gamma minus 1, and T2 dash is equal to T1 r to the power gamma minus 1 alpha, T2 dash is T1 r to the power gamma minus 1 into alpha, and the values of T3 is equal to T1 r to the power gamma minus 1 alpha rho, T1 r to the power gamma minus 1 alpha rho, and T2 dash here T1 r to the power gamma minus 1 alpha. If we put the values of this in the above expression, so the efficiency of the dual cycle will be equal to 1 minus T1 alpha rho to the power gamma minus T1 upon T1 alpha r to the power gamma minus 1 minus T1 r to the power gamma minus 1 plus gamma times T1 r to the power gamma minus 1 alpha rho minus T1 r to the power gamma minus 1 alpha. So, from here T1 will be cancelled out from numerator and denominator. So, the expression finally we will get the efficiency of dual cycle is equal to 1 minus 1 by r to the power gamma minus 1, that is the thermal efficiency of the Otto cycle, into rho minus 1 upon rho minus 1 to the power gamma into gamma to the power gamma into gamma multiplied by alpha into alpha plus alpha minus 1 plus alpha minus 1. So, this is the thermal efficiency of the dual cycle. So, 1 minus 1 by r to the power gamma minus 1 thermal efficiency of the Otto cycle, rho minus 1 upon rho minus 1 to the power gamma into multiplication in, if we multiply gamma in the rho minus 1 bracket, alpha in the multiplication of rho to the power gamma, alpha in the whole bracket multiplied in the whole bracket plus alpha minus 1 plus alpha minus 1. So, this is the thermal efficiency of the dual cycle, in the format of compression ratio R, explosion ratio alpha and cutoff ratio rho. So, this is all about the working of the Otto, diesel and dual cycle. We will continue the comparison of Otto, diesel and dual cycle in next lecture. Thank you.